All right, today we're going to talk about the derivative of a polynomial. You know, it's actually not easy, as we've seen, to take the derivative of a function. You got to do that thing with the limit as h goes to 0 of all that stuff. You got to go through a lot of steps, right? It turns out, if the function is a polynomial, it's actually really easy because of some tricks. So I want to show you the tricks, and once you know the tricks, you never have to use that limit thing, which turns out to be much harder. From now on, you're going to view that limit thing as the hard way, and what we're going to do today is the easy way. Derivative of a polynomial. Derivative of polynomials. We're going to start simple when it comes to this trick. Let's start off with the simplest kind of polynomial. That would be just a constant, like, you know, f of x equals 3 or something like this. Generally, this could be any specific number, you know, fx equals 3, fx equals like square root of 2. It doesn't have to be a really nice number, just any old number. You know, the function would look like this, f of x equals c. What is the derivative of a function that looks like this? Well, if you don't know the trick yet, you got to use the limit. Let's just do it. The derivative is the limit h goes to 0, f of x plus h. This is the usual thing, right? Minus f of x divided by h. Now my function is f of x equals c. That means no matter what you plug in, no matter what the x is, the answer is always c. All right? So let's do the thing we always do. We plug in the function. Well, the f of x, I said, no matter what the x is, the answer is always c. So this part will be c, right? Because f of x equals c. What about f of x plus h? It's a little strange, but I said no matter what you plug in, the answer is always c. That means this here, f of x plus h, is c. No matter what you plug in, if you plug in x plus h, the answer is always c, all right? Divided by h, of course, but c minus c up top is 0. So what you have here is the limit of 0 over h. 0 divided by h is 0, and so this is 0. I'm out of room. So the derivative f prime of x is 0, all right? Put this fact in your memory banks. The derivative of a constant is 0, all right? You should memorize that, I guess, but we're going to be doing this. We're going to be using this so often that it's not a problem. You're going to remember this naturally. The derivative of a constant is 0. Okay, the constant, that's the most simple kind of polynomial there is. Let's do one that's a little less simple. I'm talking about f of x equal x. Let's try the derivative of that. Give me some room. Just like a speck. Can you see that? Oh, I got it. F of x equal x is the next simplest type of polynomial. What's the derivative of that? Well, let's just do the definition as we always do. F prime of x is limit h goes to 0, f of x plus h minus f of x divided by h. All right, f of x equals x is my function. So f of x plus h, you go up here and you replace x by x plus h. The answer is x plus h, right? You replace x by x plus h. And then minus f of x is x divided by h. Simplify, can you simplify? Yeah, the x's subtract and cancel, so this just is limit h goes to 0 of h divided by h. H divided by h is 1, and so the answer is 1. So what's the conclusion? If f of x equal x, then if f of x is x, then f prime of x equals 1. All right, so the derivative of a constant is 0. The derivative of x by itself is 1. This fact you should also memorize, but again, I said before, we're going to do this so many times that you're going to remember this just kind of automatically by repetition. Okay, that was x. What about the next most complicated, or the next simplest polynomial? Let's talk about x squared. Actually, x squared is something that we have already talked about. This is one of the first examples that we did doing the derivative. If you have f of x equal x squared, the derivative maybe remember this, so you can just look back at your notes. And I got squeaks. Sorry. The derivative is 2x if f of x equal x squared. I don't know if you like this. It's kind of a pain to have to write, f of x equals whatever, and then f prime of x. Actually, there's a single way that we can write these, and I'm going to write it like this sometimes. This looks a little weird, but this d over dx means the derivative of, and the way you would write this is like this. The derivative of x squared equals 2x. All right, so this here notation means derivative of 3 dots, right? It means the derivative of x squared equals 2x. It's just a nicer way than writing like these two separate formulas here. The derivative of x squared equals 2x. What else did we just say? We also said the derivative of x equals 1, and before that the derivative of a constant equals 0. All right. What I would like to do is look at all of these derivatives and kind of sort of see a pattern. Can you see a pattern between these? I don't know if it's clear just yet. Let's talk about x to the third power. I think once we do that one also, we will see a pattern. So I want to do the derivative of x cubed. All right, derivative of x cubed is what I want to do. As always, we start with the limit. H goes to 0. F of x plus h minus f of x divided by h. Okay, x cubed is my function, so when I plug in here, I get f of x plus h. You replace x by x plus h, and it becomes x plus h cubed minus f of x is x cubed divided by h. All right, now, unfortunately, you got to expand this thing, x plus h, the whole thing cubed. You have to do like a triple FOIL thing. This is a real pain, actually. Multiply out all of that stuff. You multiply the first two out fully, and then you multiply everything in there by that one. I happen to know what the answer is. There's actually a little trick which I don't really want to talk about, but for expanding things like that. Here's what you're going to get. X plus h cubed, it turns out, is x cubed plus 3x squared h plus 3xh squared plus h cubed. That's what you get if you expand this thing out and resimplify everything, recombine all the terms. This is what you get. Okay, that was just this part, x plus h cubed. Then I see from before minus x cubed divided by h. Okay, now we simplify. Hopefully some of this will cancel. Not much, actually. You just have x cubed and minus x cubed. They cancel each other. And what remains is all of that stuff. Like we usually do, I'm going to factor h out of everything. You notice each of these three things has some h's in it. So I get limit h goes to 0. All right. Factoring h out, it's 3x squared on the first one plus 3xh, right? This had a h squared, so I take one of the h's out, one remains, plus h cubed becomes h squared when you factor one of the h's. All right, and now, like always happens when we finish one of these, you cancel the h's, and then what remains, you take the limit as h goes to 0. Almost there. All right, what do we get when we take the limit as h goes to 0? You can just plug in h equals 0 everywhere, and you get 3x squared plus 3x times 0 plus 0 squared. These are both 0, so the answer is 3x squared. That is the derivative of x cubed. All right, let's sort of write all those down together and see if we can see the pattern. We already said the derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed, that's the one we just did, 3x, come on now, 3x squared was the answer. 3x squared. All right, do you see the pattern? What is the derivative, for example, of x to the 4? There's a little pattern here. Can you tell what it is? What'd you think? That was not a freeze frame, by the way. What do you think when you do the derivative of x to the 4? It turns out what you get is 4x to the third. See, the pattern is this exponent comes down and becomes a coefficient in the front, like this 3, and matches this 3. That is not a coincidence. And then the exponent decreases by 1. That's how you do this. So the 4 comes down to the front and becomes a coefficient, and then you decrease the exponent by 1. All right? This is the pattern, and this is sort of the ultimate trick for doing the derivative. It means that whenever you're taking the derivative of some power of x, you can just say the answer immediately. You don't really have to go through that whole limit thing. You know what the answer is going to be. It's going to be like that. If I was to write this out in a formula, it looks something like this. Derivative of x to the power n is what I said. What happens is the power becomes a new coefficient. So you're going to see n in the front, and then x, and then what is the new exponent? The exponent gets decreased by 1. So this is the formula for the derivative of a power of x. This is called the power rule. You're going to be using it so often you won't even really think of it as a rule. It's just the thing you do when you take the derivative of a power of x. All right? This actually works. Now, we only talked about this for like whole numbers for the n, 2, 3, I wrote 4 before. Actually, this works for any n. That is, it doesn't have to be a whole number. It can be any exponent up there. Like, let me just say, even negative numbers or fractions. All right. This works for any n, so it's actually extremely applicable in lots of different ways. For example, what is the derivative of something like 1 over x to the 4? Well, this doesn't look like just some power of x, does it? Well, actually, I hope you know, this is actually the same as x to the minus 4 power, right? That's what 1 over x to the 4 is the same as x to the minus 4. That's what x to the minus 4 means. So, since I rewrote this to look like this, x to the n, I can use the formula, and I get, what do you get? The exponent becomes a coefficient, so it's minus 4 in the front, and then the x, and then you decrease the power by 1. Negative 4, you subtract 1, you get negative 5. All right? And that is the derivative of 1 over x to the 4. Okay? All right, let's try one more example. Here's another one that looks a little weird at first, but you realize that it is actually just a power of x. Is there any way to rewrite square root of x as some power of x? Yeah, there is. It's x to the 1/2 power. In fact, this is a theme throughout basically this whole course. It is essentially never helpful to write a square root with the radical sign. It is always, whenever you see a square root in this class, you should always immediately rewrite it as a 1/2 power, because this is a much more convenient form for taking the derivative. Anyway, now we use my formula, right? Not my formula, our formula. It's everybody's formula. You move the exponent down to the front. It becomes the new coefficient. You put the x, and now you decrease the power by 1. What is 1/2 minus 1? It is negative 1/2. And that's the answer. So you do the same thing. You move the exponent. It becomes the new coefficient. And you decrease the exponent by 1. In this case, 1/2 minus 1 is negative 1/2. All right. So powers of x is real easy to take the derivative. What about something that's not exactly a power of x, but like pretty close, like something like 7x squared, okay? This is not just x. If it was just x squared, the answer would be 2x because of this trick. But what about the 7? Does that 7 really make a big difference? The answer is no, actually, it doesn't really make a big difference. It does make some difference, but it's not a big deal. Let's talk about this in general. I would like to know, what is the derivative of some constant times f of x, right? What I'm talking about here is the x squared we already know how to handle. What effect does that 7 have? In general, the question is, if you just multiply something by some constant, what effect does that have on the derivative? It turns out it has a very simple effect, which can be very helpful. Let's talk about this. Now, since we don't already know what that is, the only way to figure this out is to use the limit definition. this is probably the last time that we're going to actually find the derivative of something using the limit. What is this? With the limit, it's limit h goes to 0. I do f of x plus h, but here my function is c f of x. So it's c f of x plus h minus c f of x divided by h. Okay, can you do anything with that? You know, usually at this point, we would plug in the function f, but we don't know what f is. We're just going to leave the f. Can you simplify anything here? There's only one thing you can do, and that is you can factor a c out on top, and in fact you can factor the c out of the entire fraction. So it says lim h goes to 0, c times f of x plus h minus f of x divided by h, right? What is that? Does that look like anything to you? Actually, it looks like something to me. This fraction right here is just the derivative of f of x when we take the limit, right? That's what you write for the derivative when you're using the limit definition of the derivative. So this, when you take the limit, the c is just c, whatever it was before, and this right here is the derivative, f prime of x, okay? So the moral of the story, the derivative of c times f of x is equal to c times the derivative of x. Another way you could write that is like this. Derivative of c f of x is equal to c times the derivative of f of x. Squeaks, right? Basically what I'm saying is if you have a constant and you're taking the derivative, the constant just stays in front of the answer and otherwise it has no effect on the derivative. For example, specifically what I asked about before was what's the derivative of 7x squared? Well, if you believe what I said, the 7 just stays in front of the answer, and then you write the derivative of x squared, which is 2x. So it's like that, 7 times 2x, which you could say 14x. All right? This is how you handle a constant multiple in the derivative. It's very simple. That constant multiple just becomes a constant multiple on the answer, and nothing else happens, really. For example, what would it be if it was, 25x to the 4? Well, the derivative of 25x to the 4. The 25 just stays in front of the answer, and I do the derivative of x to the 4, which is 4x cubed. And we get 100x cubed. All right, that's all there is to it. Actually, you can do this whole thing in your head. Usually people don't think it through in 2 steps. Usually the way you think this through is you look at this derivative, 25x to the 4. When you take the derivative, the 4 comes down and multiplies onto the 25, and you get 100. Then you decrease by 1, and you get x to the 3rd. All right? This is how you should think about that. So the derivative of something like 20 square root of x. As always, we rewrite the square root as a 1/2 power. This is 20x to the 1/2. And now I'm going to move the exponent down to take the derivative. 1/2 times 20 is 10. And then x to the minus 1/2. You decrease the power by 1. All right, that's how we do it. A constant times the power of x is easy once you know the trick. We know how to handle a single constant times the power of x, but a real polynomial, looks something like this. Like that's what a polynomial is. It's each one of these individually we know how to take the derivative, but how do you take the derivative of the whole thing when they're added together, or subtracted in this case? It turns out the best thing possible happens here. So here's another formula about what is the derivative of 2 things added together. All right, that's really what we're talking about here. Here it's 3 things, but it doesn't actually matter. What is the derivative of 2 things added together? It turns out you can figure this out, work this out using the limit. Again, I don't really want to go through the details like I did for the constant. It turns out what you get is just this, derivative of f of x plus the derivative of g of x. What this means is when you have stuff added together and you want the derivative of the whole thing, you can just take the derivative of the individual parts and add the answers together. All right, what that means is, for example, this here, the derivative of that example, 3x to the 7 plus 5x squared minus 3x, we can simply just go down the line here and take the derivative of each part and add all the answers together. So I'm going to take the derivative of 3x to the 7. I get 21x to the 6. The 7 multiplies by the 3 to be 21. You decrease the exponent. 7 becomes a 6. Then I just immediately add this one. We move the 2 down, we get 10x to the 1, which is x. And then I do this one, minus 3, and then the derivative of x is 1. That was part of our list of things. So it's 3 times 1, which is just 3. 3. Why'd I do that? How you like that? The derivative of a polynomial. This was our goal for today. It turns out to be real easy, all right? You just do that trick in each of these parts, and then you add all the parts together, and that's all there is to it. Let's just try a couple more examples. All right, 2 more examples. I got an easy one and a hard one. Here's an easy one. How about the derivative of x to the 10 minus 3x squared plus 5x plus 2. This is the easy one. It's just like the one I said before. You just go down the line here, taking the derivative in each part. So x to the 10 becomes 10x to the 9. Negative 3x squared becomes negative 6x to the 1. The 6 comes from multiplying 2 times 3. 5x becomes 5. That's because the derivative of x is 1. Plus 2. This is the first thing we talked about. What is the derivative of 2? Just a number by itself. The derivative of a constant is 0. And so here I just get plus 0. I'll write it here, but you don't have to write that. Plus 0. This is the answer. 10x to the 9 minus 6x plus 5. All right? I said that was the easy one. Once you know how to do this, I hope you agree this is easy. Once you know the trick, you can basically just write the answer as fast as I wrote the question, right? There's nothing hard about this at all. A little trickier. How about the derivative of, let's say, x to the 6 plus 3 root x minus x divided by x squared. How you like that? What's hard about this one is this thing divided by x squared. If it was just that on the top, this would not be so difficult. But the fact that we're dividing everything by x squared really messes it up, all right? Let me just say you cannot just take the derivative of everything on the top and then also take the derivative of the bottom. Individually, the top and the bottom, you can easily take the derivative, but that's not allowed. You'll get something, but you'll get the wrong answer. There are special rules and special tricks that you have to use when you are taking the derivative of a big fraction like this. Since we haven't learned those rules yet, we're going to try to do this the old-fashioned way, not using the limit, but try to simplify this somehow and turn it into a polynomial. That's the idea. Is there anything you can do to simplify? Well, first thing you should do, you should just do this like instinctively. Instead of root x like this, you should write it as x to the 1/2 power. That doesn't address the immediate concern, which is the division by x squared, but I'm going to write it like this, x to the 6 plus 3x to the 1/2 minus x. Here's the real trick that I'm going to do. Instead of dividing by x squared, I'm going to write this like multiplying by x to the negative 2. All right? That's the same. Dividing by x squared is the same as multiplying by x to the minus 2. What's the point of rewriting it this way? The point is now you can distribute the x to the minus 2 across the whole thing. So it becomes, I didn't do the derivative yet. That's why I'm still writing d dx. The last step is when I'm going to actually do the derivative. Anyway, what is, I'm distributing the x to the minus 2. You remember what happens when you multiply x to the 6 times x to the minus 2? You add the exponents. So in this case, actually, you subtract 2. So it'll be 6 minus 2 in the exponent, which is x to the 4, right? Plus 3, here I have x to the 1/2, x to the minus 2. You add the exponents, it's going to be 1/2 minus 2. That's negative 1.5, right? 1/2 minus 2 is negative 1.5. And then minus x times x to the minus 2 becomes minus x to the minus 1, all right? Also known as 1 over x, but you shouldn't write it that way. This is much more convenient for taking the derivative, all right? Now it does look like a polynomial. There's a weird exponent here, but it's just a bunch of things added together, each of which is a power of x. So we can take the derivative using our trick. So this is 4x cubed. Right here I multiply negative 1.5 times 3. That's a weird number, I guess. What is it? 4.5, I think. Negative 4.5 x. And now I decrease the exponent by 1. Makes it negative 2.5, right? Negative 1.5 minus 1, negative 2.5. And then minus, you bring the exponent down, so it's negative 1 times x, and then the new exponent, you subtract 1. Negative 1 minus 1 is negative 2. All right, that's the answer. It's written a little strange. If you want to clean this up a little bit, I don't really care, but it's like this. 4x cubed minus 4.5x to the minus 2.5 plus x to the minus 2. There you go. That's the derivative of this weird thing up there. All right, all right, all right.